Hello everyone. In this video, we will talk about the importance of 3D element order and topology in ANSYS Mechanical. When meshing an assembly, we may notice that some parts are meshed with hexahedral elements, while other parts are meshed with tetrahedral elements. Is there a difference in the results? Is one type recommended over another? In fact, we may also hear from others that in finite element analyses, hexahedral elements are preferred over tetrahedral elements. Is this always true? In this video, we will answer all these questions and clarify the use of different element types for linear structural analyses. Let's get started. Let us first focus on how the mesh is generated for 3D solids in mechanical. When generating the mesh on solid bodies, depending on the complexity of the geometry, the mesh may consist of one or more element shapes. For instance, simple block-like geometries are sweepable. A sweepable body is one that has two opposing, topologically similar faces. In such cases, one face is meshed using quadrilaterals, and this 2D mesh is essentially extruded to the opposite side to create a hexahedral mesh. As evident, it is easy to generate a good quality hexahedral element for sweepable bodies. Hence, mechanical by default detects such sweepable bodies and generates hexahedral meshes. However, if we add fillets to the same block, then hexahedral elements are no longer able to capture the curvature unless we use a very large number of elements. In such cases, when the geometry is not sweepable, we may need to resort to using all tetrahedral elements as seen in this example, or we may have to use a combination of tetrahedral and hexahedral elements. When such situations arise, which is common in practical applications, it is important to understand how the different element types may affect the results and how to use that knowledge to inform our choice of element shape and order. But before that, let's first understand the basic attributes of a solid element in a 3D stress analysis. A solid element is made up of nodes where each node has 3 degrees of freedom, displacements in x, y, and z directions. The displacements and reaction forces for the element are calculated at the nodal locations. In addition, there are integration points within the element where the strains and stresses are calculated. The strains are calculated based on corresponding displacements at integration points that are determined by interpolation between the nodal locations. These interpolation functions are called shape functions. These concepts are common for all the solid elements that are used in a stress analysis. Now let us take a look at 4-noded tetrahedral elements. Why are we asked to avoid these elements in linear analyses? A 4-noded tetrahedral element is also known as a lower order or linear tetrahedral element, since the shape function is a linear polynomial. It's worth taking a moment here to explain that we use the term linear in different situations in finite element analyses. Linear analyses assume small deflection theory, while a linear element describes an element with a linear shape functions, but we should not confuse the two, as a linear or lower order element could still be used in a nonlinear analysis. So, going back to our topic, lower order or linear tetrahedral elements suffer from the following. Firstly, they have one integration point. So, strain and stress are calculated only at one location, and it is assumed that strain and stress at any other location in the element is same as that at the integration point. Hence, 4-noded tetrahedral elements are constant strain elements, and an extremely fine mesh may be required to capture the strain and stress gradient accurately. Secondly, in case of bending dominated problems, linear elements are prone to shear locking since they are unable to accurately capture the curvature of the actual material under bending. This introduces spurious shear stresses in the part, and its response is overly stiff regardless of how fine the mesh is. Due to these reasons, regular lower order or 4-noded tetrahedral elements are never recommended for linear stress or dynamic analyses of solids. Linear 8-noded hexahedral elements do not suffer from these issues, so they are a good alternative to 4-noded tetrahedral elements. Hence, if our choice was limited to lower order elements, then linear hexahedral elements are fine, but linear tetrahedral elements should be avoided. Are we limited to linear elements though? In the past, users of finite element analyses were in fact often limited to using linear elements due to lack of sufficient computational power. However, due to advancements in numerical methods and computational resources, we presently use higher order elements without having to worry about the computational costs. Higher order elements are elements whose shape functions are quadratic. The limitations we discussed previously are resolved by using these quadratic or higher order elements. Quadratic elements are defined by introducing mid-side nodes into the linear element. This results in a 10-noded tetrahedral element or a 20-noded hexahedral element. Let's see how adding mid-side nodes and using quadratic shape functions help the tetrahedral element overcome its previous shortcomings. Second-order tetrahedral elements have 4 integration points, meaning that strain and stress are evaluated at 4 locations in the element. Hence, strain can vary within the element, so it can capture the stress and strain gradients effectively. In case of bending dominated problems, the additional mid-side nodes also help to capture the curvature present in the actual material. So second order elements do not generate spurious shear stresses and shear locking is not an issue. Therefore, it's acceptable to use a mesh consisting of only tetrahedral elements or a mix of hexahedral and tetrahedral elements in linear stress or dynamic analyses of 3D solids, provided they include mid-side nodes. In fact, a good quality tetrahedral mesh performs better and provides more accurate results compared to a distorted hexahedral mesh. Hence, the use of second-order tetrahedral elements or hexahedral elements is recommended in linear structural analyses. Note that considerations may differ for heat transfer analyses or non-linear structural analyses, but we are limiting our discussion to linear structural analyses in this video. In addition to the tetrahedral and hexahedral elements, there are 2 more 3D elements which may be generated as part of a mixed mesh. They are the wedge element and the pyramid element. Having an excess of either of these element types could lead to spurious stress results, so it is acceptable to have them in the mesh as long as their count is very small in comparison to the other tetrahedral or hexahedral elements. If their count is significant for a particular geometry, then it's recommended to mesh the part using all tetrahedral elements. Now that we understand the different elements, we note that by default quadratic elements are used by mechanical when meshing 3D solids due to their numerical accuracy as noted earlier. If sweepable bodies are found in the geometry, by default mechanical meshes them with a mesh that predominantly consists of hexahedral elements and possibly a few wedge elements. For bodies that have an irregular shape or complicated geometries, mechanical generates a tetrahedral mesh. So why does mechanical choose these defaults? Sweep meshing geometry, when possible, is an efficient way of providing a relatively uniform mesh, which is why mechanical meshes sweepable parts with hexahedral elements by default. If you have thin mesh sweepable parts, sweep meshing also provides an added advantage of being able to control the number of elements through the thickness if needed. This is not always necessary, but an attractive feature of sweep meshing. However, if the geometry is very complicated, sweep meshing cannot be used to generate a hexahedral mesh. In such cases, quadratic tetrahedral elements can mesh the body with relative ease without requiring the geometry to be subdivided. Apart from being able to mesh complex geometries, another advantage of using tetrahedral elements is that mesh transitions from a coarse mesh region to that of a finer mesh are possible without much effort. This allows us to generate an optimal mesh so that we can invest more nodes and elements in the regions of high stress gradients, for example, and mesh the less important areas with fewer nodes and elements. On the other hand, hexahedral meshes are created by sweep meshing, and hence the mesh refinement propagates throughout the sweeping direction. Since the default order of elements is quadratic, and we have seen that there is no real preference of one type of quadratic element over the other, for most linear analyses, the element types utilized by ANSYS Mechanical is recommended and should not be changed. Of course, we usually would want to define the element size or define local mesh controls, but in most cases there is no need to subdivide or simplify a geometry in order to get an all hexahedral mesh, as that is not needed to get a computationally efficient and numerically accurate model. Let us now proceed to the demo and compare the results for two identical models when a hexahedral mesh is used for one case and a tetrahedral mesh is used for the other. Here we have two identical assemblies of pin joints. The two cases have identical geometries, materials, loads, and boundary conditions. Each assembly consists of a cylindrical pin and a block through which it passes. Our objective is to examine the stresses that the two pins develop when the block is held while the pin is pulled 0.02 millimeters in a given direction from both ends. All parts are made of structural steel. A frictionless contact region is defined between the pin and the cylindrical hole of the block in both cases. Identical loads and boundary conditions have been defined for the two assemblies. A face of each block is fixed. Remote displacements with rigid behavior are applied to the top faces of both the pins. We have applied a displacement of 0.02 millimeters in the x direction for both the faces. Remote displacements in y and z directions are free, and rotations about all three axes are free for the top faces. We have also applied remote displacements with rigid behavior to the bottom faces of the two pins. A displacement of 0.02 millimeters is defined in the x direction. The displacement in y direction is left free, but displacement is constrained in the z direction to prevent the pin from sliding out. Rotations about x and y axes are left free, but rotation about the z-axis is constrained to prevent the pin from rotating. For results, we want to calculate the total deformation for all the bodies and the equivalent stress for the two pins, which are the bodies of interest. We now want to see whether meshing the pins with tetrahedral elements or hexahedral elements gives us similar stress results or not. Based on the loads defined here, the contact regions between the pins and the blocks are the regions of interest. So we need a finer mesh in that region. In other areas, we can have a coarser mesh to save some computational time. Let's set the global mesh controls. Click on Mesh. Under Details, leave the element order as program controlled. As you may recall, ANSYS Mechanical uses quadratic or second order elements by default for the solid bodies. Set the element size to 2 mm. These are global settings that will be applied to all the bodies unless some local mesh sizing control overrides them. If we right-click on Mesh and select Show Sweepable Bodies, we can see that all 4 parts are highlighted, indicating that Mechanical views all bodies as sweep meshable. We will mesh the pin in the first assembly with hexahedral elements and the one in the second assembly with tetrahedral elements. Right-click on Mesh, Insert, Sizing. Pick the top and bottom edges of the pin in the first assembly and click Apply. This will specify a finer mesh around the perimeter. To mesh the pin in the second assembly with tetrahedral elements, right-click on Mesh, Insert, Method. Activate the Body Select option, select the second pin and click Apply. Set the method to tetrahedrons. Since our region of interest is the portion of the pin which is in contact with the block, we will insert contact sizing. To do this, simply drag and drop the second frictionless contact pair to the mesh branch. Change the element size to be 1 mm. This creates elements of size 1 mm closer to the contact region. Now right-click on Mesh and click Generate Mesh. Let's take a look at the mesh on the 2 pins. The mesh on the first pin looks quite uniform throughout the length of the pin. In the case of the second pin, the mesh is finer in the region where the pin comes in contact with the block and is coarser in other regions. Let's also see if the element size varies along the radius of the pin. We use section planes to visualize this. Go to the Home tab and click on Section Plane. We need to draw a line which, when extended out of and into the screen, gives the cutting plane. We create a section plane cutting through both the assemblies by drawing a line as shown. Section plane definitions and properties can be edited in the Section Planes window. Activate the Show Whole Elements option for easier visualization, especially of the tetrahedral elements. To move the cutting plane or show the geometry on the other side of the cutting plane, select the section plane and click on Edit Section Plane option. You can click on the dotted line to show the portion of the pins that is on the other side of the cutting plane. You can drag the blue square along the cutting plane normal to change the location of the cutting plane. When we look at the mesh on the first pin, we see that it is uniform throughout its length. Since hexahedral mesh is generated by sweeping the mesh from one end of the pin to the other, we cannot generate a hexahedral mesh with smaller elements in the center of the pin and coarser mesh in the regions away from it. For the second pin, when we look at the mesh variation in the axial direction, we see that the mesh is finer in the center of the pin. If we look at the variation in the radial direction, we see that the mesh on the top and bottom faces is uniform, But in the contact region, the mesh transitions smoothly from larger elements in the center of the pin to smaller elements closer to the contact surface. Thus, we can see that tetrahedral meshes can transition more easily from a coarser mesh to a finer mesh. Now let's see how many nodes and elements we have on each assembly. For this, click on Geometry in Tree Outline and then go to the Home tab, Worksheet. We can see the nodes and elements on each body for the current mesh. We observe that the total number of nodes and elements is higher for the first assembly, which is meshed with hexahedral elements, as compared to the second one meshed with tetrahedral elements. Due to being able to transition smoothly from a coarse mesh to a finer mesh, the tetrahedral mesh also has fewer number of nodes and elements, since we are able to invest more nodes only in the region of interest and use fewer nodes and elements in other regions. Let's solve this model and compare the results for the two assemblies. Right-click on Solution and click on Solve. When we look at the total deformation, we see that the contours on the two assemblies are very similar. If we look at the equivalent stresses on the two pins, we again see very similar contours. The maximum equivalent stress is also very close when the two cases are compared. Since we use the default element order, which is quadratic, we compared second order tetrahedral elements to second order hexahedral elements in this demo, and we can see that the numerical accuracy is similar. This concludes the demo and brings us to the end of the video. Before we wrap up, let's summarize the key takeaway points. Various 3D elements are available to mesh solid bodies. Tetrahedral and hexahedral are the two element shapes that are used most widely. The shape functions of an element determine its order. We can use linear elements which have nodes only on the vertices of an element, or we can use second order elements which also have mid-side nodes. Tetrahedral elements suffer from some shortcomings, such as being constant strain elements and being prone to shear locking. Hence, linear tetrahedral elements should be avoided in linear stress or dynamic analysis. Thanks to today's computing hardware and advances in solver technology, we can use second order elements without worrying about the computational costs. When it comes to second order elements, a quadratic tetrahedral mesh performs as well as a quadratic hexahedral mesh. Tetrahedral meshes offer the added advantage of being able to mesh complex geometries easily as compared to hexahedral elements which require a sweepable body. Tetrahedral elements can also transition smoothly from a coarse mesh to a finer mesh. Due to this, we can easily define a finer mesh in the regions of interest and a coarse mesh away from it. ANSYS Mechanical uses second order elements by default and meshes sweepable bodies with hexahedral elements and other bodies with tetrahedral elements. Based on the previous 2 points, we can conclude that if ANSYS Mechanical generates a tetrahedral mesh for any part, in most cases, there is no need to spend time subdividing or simplifying the geometry to get an all hexahedral mesh. Despite the visual differences between quadratic hexahedral and tetrahedral elements, both provide good numerical accuracy. So we need not worry that sweep meshable parts are meshed with hexahedral elements while other parts are meshed with tetrahedral elements. This concludes the video. Thank you for watching and do visit our channel to discover more useful learning resources.